sort of Friston framework. The idea here is that systems minimize variational free energy, which is a sort of long-term error or surprisal. And these approaches look to neuronal dynamics or organization of neuronal populations or organization of cortical areas or organisms or even swarm behavior. And then we fit prior data or we run simulations, but it's not an experimentally motivated approach. Some proponents of this, other than Friston, include Jacob Hoey, Andy Clark, Anil Seth, Liz Feldman-Barrett, and so on. And then there's this other approach that we take to be characteristic of the Tenenbaum and Griffiths and Goodman kind of work. We call it, so rational constructivism is their term for the developmental theory here, which is Xu and Gopnik and so on have popularized this. But in this sort of general Tenenbaumian framework, we have Bayesian models of optimal behavior, optimal computations, which are formalized, and we use these to generate hypotheses and then run behavioral experiments for them. This approach is typically understood to be a kind of rationalist or nativist approach and posits representations, abstract representations, and computations thereon. These have traditionally been understood to be theories. So people have been arguing over the theoretical commitments of these accounts and ask about what predictions they make and inquire about their empirical support and so on and so forth. We take theories in general to be, I ran an informal survey this, I've been, prior to this, I was at a number of academic events that were really interrogating what a theory is in cognitive science and psychology and neuroscience. And so I've been puzzling over what the sort of scientist on the street takes a theory to be. So I ran a little informal survey this week and got maybe like 250 results on this, and the common threads were that people take theories to be unificatory, explanatory, and descriptive. And in so much as any conceptual tool at use in science is taken to be truth apt, is taken to be truth valuable, this seems to apply to theories in the common conception. On the other hand, modeling frameworks we take to be collections of formalisms that run together, and then standardly a kind of toolbox of ways of using, ways of employing this formalism in science and ways of interpreting it, ways of construing it such that it relates to the phenomena. But models themselves and modeling frameworks as collections of models are not themselves truth valuable things. So we argue that rational constructivism plus and the variational free energy minimization approach are not, in fact, theories of cognition, but are rather better understood as modeling frameworks. So under this view, there are certainly standard ways of construing rational constructivism and variational free energy minimization that relate to them to the phenomena that we're studying, but there's no essential theoretical or conceptual or empirical commitment to these approaches. So we can't interrogate what the truth value of a modeling framework is, or to what extent it's the right approach. Rather, they're simply different ways of approaching kind of natural phenomena that employ different idealizations, but there's no right approach. We also want to point out, the talk that we had before lunch really nicely summarized this, that these are optimality modeling approaches, and optimality modeling is really aimed at exploratory modeling. It's when we don't quite fully understand the phenomena of interest, we employ optimality modeling, we employ optimality assumptions as a kind of modeling gambit or idealization to kind of get our foot in the door empirically. But the assumption of optimality, importantly, itself is never put to the empirical test. That's never what's being evaluated when we do experimental work that's in alignment with an optimality modeling approach. And we also note that in the history of science and philosophy of science, there's been a lot of debate over what is commonly called mechanistic explanation or causal mechanistic explanation, or top-down versus bottom-up modes of explaining phenomena, that go back at least as far as the 18th century, right? At least as far back as the debate between the Newtonian approach versus the mechanists who were coming before him. You can see this in things like Tinbergen's Four Questions in Ethology, Newton versus the mechanists, of course, the debates over laws of nature and what constitute laws of nature in physics and so on, new mechanism in philosophy, etc. And however, as Angela Potocznik pointed out in a 2018 book chapter that seemingly no one has read, as no one's really cited it, there is a focus, a sort of univocal focus in the philosophy of science literature on explanations on the sort of contingencies in nature that types of explanations point out. So when we talk about varying accounts of explanation, they only seem to vary, at least if the popular literature on philosophy of science of explanations holds, according to what contingencies they pick out. So something like causes or something like constraints or what have you. And Angela points out like 8 additional dimensions along which explanations vary. And so in a similar spirit, I think what we're picking out by this debate between top-down versus bottom-up explanation versus mechanistic, or mechanistic versus non-mechanistic explanation, is actually something with at least 2 axes. There are at least 2 kind of lines of variance along which mechanism is being debated that haven't really been addressed. So one of these is kind of Dirac, top-down, bottom-up, or an ontic, top-down versus bottom-up understanding. So on this view, higher order emergent properties of some natural phenomena are explained in virtue of lower order properties, in virtue of, for example, the material composition of the thing you're looking at, right? In the case of variational free energy minimization, it's that large-scale or behavioral traits are understood to be the result of Bayesian dynamics at lower order scales, for example, neuronal dynamics or neuronal populations or cognitive architectures, information flow in cognitive architecture, what have you. The bottom-up, or rather the top-down version, is that low order properties are explained in virtue of higher order constraining properties. So under rational constructivism, computations performed in the brain are understood to be the product of the Bayesian dynamics at the higher level, at the behavioral level. Yeah, it doesn't make that slide. Ooh. Yay! So on the Dedictor reading, however, the Dedictor version of this dichotomy is that one sees constraints or transcendental conditions of existence for some explanandum, for example, principles that constrain behavior. So under VFEM, this is a kind of, the explanatory structure is a sort of transcendental structure. So the minimization of variational free energy is understood to be a kind of constraint placed on the existence of living or cognitive systems under this approach. And this is the assumption from which we proceed in analyzing behavior. On the other hand, the reverse of this is that you have observables and then you derive the higher order explanatory principles from those observables. So under the rational constructivism framework, we're fitting models to behavioral data, like we're fitting Bayesian optimality models to behavioral data, and we reason about the computations, about the low order phenomena that follow from there. So I improvised this morning a sort of political compass on which to visualize this. I don't know if that's helpful, but we find that these are one way of conceptualizing what separates these 2 modeling frameworks is that they're sort of inverses of each other along these axes, right? And a note on idealization, since I have the pleasure of having Liam Bright in the audience, he once said to me that I seem to have a sort of bourgeois aversion to idealization in science. I seem to require too much detail or factivity or what have you, and I like to think of myself that I embrace the need for idealization. However, I also certainly hold to the belief that certain areas of science and certain scientific practices are very good at kind of instrumentally employing idealizations in order to answer specific questions about the phenomena under study, and then de-idealizing their modeling approaches when it comes to interpreting them, when it comes to deriving results from them. When it comes to the part where we milk the knowledge out, right, we're good at de-idealizing. And other areas of science or other scientific practices play much more fast and loose with idealizations, such that when it comes time to interpret the results of these scientific practices, you can get a sort of deceptive practice here where we forget to de-idealize, or we don't bother to de-idealize. And this is of concern to me. And so in relation to these two frameworks, I think in relation to optimality modeling in general, this is an area where a lot of caution is needed, because it is an exploratory method, and it is lacking in resolution in the way it goes about exploring this phenomena, and requires a lot of carefulness in the interpretation. And so I want to urge that. And I'll turn it over to Wiktor to talk more about idealization.
Yeah. So I'll start by saying that I do not entirely agree with Mel.
We've been fighting, can you tell?
Yeah. So
you're not on screen.
Right. So instead of claiming that, so whereas I agree that this kind of normative principle that in general we should avoid using idealizations in a deceptive fashion where they can be used to kind of change how the public perceives science, for example, there is this need of de-idealizing results before bringing them, giving them out to the world. However, as Angela Potocznik in her 2017 book has argued, and I wholeheartedly agree with that, within the general model-based view on science, the model-based philosophy of science, we have to treat idealizations as Potocznik writes, rampant and unchecked in science. So in fact, Potocznik argues that although there's been different debates, people have been trying to come up with different typologies. I will go through them in a second because I think it's important to kind of provide the structure for our discussion of idealization. In fact, what science does, it rarely moves from an idealized account to a less idealized account. Rather, as she writes, the idealizations are rampant and unchecked, so that in each part of science we can see a plethora of various idealizations, and if these idealizations do not prove to be delivering the results that we've been hoping they would, what scientists do, rather than de-idealizing, they move to a different set of idealizations. So this kind of, she identifies this kind of dynamic in science, and I think that whereas we can discuss whether this is a normatively good way of doing science, it seems to be the dominant way of scientific practice these days. So to kind of like, because the word idealization has popped out several times, and I think it's important to also define what we mean by idealization. So I follow here Potocznik on saying that idealizations are assumptions made without regard for whether they are true, and often with full knowledge that they are false. And as I said again, within the model-based philosophy of science, we can kind of come to grips with this idea that science is not arriving at all times at truth, but rather via, as Wimsatt has been writing, via providing various misrepresentations of reality, in cases where we know where potential falsities come in play in those misrepresentations, we can use the different ways that science lies about the world to develop a more robust, more realistic picture of the world from different models proposed by science. And
we use many false models to triangulate.
Yes.
Right.
Yeah. And these kinds of typologies or idealizations, because there's been at least two kinds of typologies proposed. The more popular one, I think, dates back to Weisberg, who has proposed three types of idealizations: the Galilean idealizations, and these are simplifications that we introduce because modeling the world more precisely is intractable. So, for example, modeling planets as point masses is a kind of is an example of idealization, of Galilean idealization. And Weisberg has proposed that, or frictionless particles is this type of idealization. And Weisberg has proposed that during the development of science, we will generally give up Galilean idealizations and instead opt for more precise, better ways of describing nature as methods and mathematics develop.
So that's importantly, that's importantly, the Galilean model for Weisberg for Michael is a model specifically of de-idealization in the progress of a science.
Yeah.
Right. So when I'm talking about de-idealization, I'm talking about the de-idealization of the use of a specific idealized conceptual tool.
Right. But as Potocznik has argued, there's very limited number of Galilean idealizations in science, and rather they fall, if any, and rather they fall under. Well, they could fall under the other two types identified by Weisberg: minimal idealizations, which we use to kind of develop the kind of minimal models that we can study. For example, as we've seen in Simon's talk before lunch, this kind of the driver example can be treated as a minimal model of a particular type of behavior in which we abstract away from various complexities and instead provide a proof of principle. And the third kind that Weisberg proposed had been the multiple model idealizations, in which case we provide various models, and each of those models idealizes the nature in a different way, and then we can kind of try to triangulate the truth, or what have you. Rower and Rice have introduced a fourth kind of hypothetical pattern idealizations, which fall between minimal idealizations and multiple model idealizations because they are single. So they have the kind of characteristics that multiple model idealizations have, but instead of focusing on providing different types of idealizations, here we just provide one. However, Potocznik argues that, in fact, so we have very few Galilean idealizations. We have very few minimal idealizations, and most fall somewhere between minimal and multiple model or hypothetical pattern idealizations, and this kind of typology does not pick out the relevant differences between them. So instead, Potocznik proposes to categorize idealizations depending on the scientist's reasons to idealize. And she has proposed this kind of like two-axis distinction between temporary and permanent idealizations, and so this would say whether we can expect this particular idealization to be supplemented or replaced in future, and from the sources that they can come from. So first, due primarily to the world, and second, due primarily to scientists' features. And for example, due to primarily to scientists' features, we can see that a temporary idealization is that of limits of computational power. So what I want to suggest is that when we move to the topic of idealization for optimality modeling, neither of those two categorizations does not fully capture the reasons that scientists idealize for and the types of idealizations they use. Because like in case of optimality modeling, probably all of the it's hard to say whether the idealizations that we make are primarily due to the world or primarily due to the scientist's feature. But definitely we can say that they are all permanent. So on one of these axes, we can decide that it's going to be impossible to de-idealize optimality models assumptions because of the nature of the optimality modeling. However, they have this kind of mixed origin, so that we both think that they are partially due to the world and partially due to scientist feature. And that's why I think that this classification proposed by Potocznik in that specific context fails. So instead, I started wondering whether we even can talk about idealizations in the context of optimality modeling. Because idealizations are a particular type of modeling choices. So choices that we make to represent particular features of the world that we can then develop our models or eventually theories on. However, idealizations differ from other modeling choices in that they are misrepresentations and distortions. And as I think has become clear in previous talks today, optimality models, specifically in neuroscience and in cognitive science, are representational only to a limited degree, if at all. This is not true, for example, for evolutionary research, where we actually can say that this is again a point made by Potocznik in a paper from 2009, where she argues that there is this particular strong view of representational character of optimality assumptions and optimality models. But in the case of neuroscience and cognitive science, I don't think we, and this, I think this has been nicely indicated in the first talk, that this representational character is unclear of optimality models. So instead, I would rather opt to this talk in the context of optimality models, such as Bayesian models of cognition, about formal modeling choices that scientists make. And these can be distortive, they can misrepresent reality. So in as much as we take them to be representational, they do misrepresent. So I would argue that they can be analyzed as idealizations. But what is nice about them is that those errors, when we know the type of idealization that we are making with the types of idealizations that we are using, we can treat errors they introduce as systematic. And this again goes back to the model-based philosophy approach and Wimsatt's seminal book from 2007, where he indicates a long list of various sources of systematic error and shows how this kind of systematicity of error in science is what makes it actually capable of, despite being false at face, to be this kind of realistic and at least truth approaching enterprise. And an important point that I want to make here that I'm unsure it has been made previously, in case of formal modeling choices, specifically in optimality models, but this probably goes beyond, we can see that they easily become entrenched. What I mean by that is that whenever we make a very, and I will move to an example maybe already, because here's a couple of modeling choices that are made in the Bayesian brain framework and specifically for VFEM and RC+. So in the case of the Bayesian brain framework in general, scientists often make these assumptions that brains represent probability distributions. And this stated as this kind of general principle seems a little bit absurd to treat brains as representing probability distributions. However, because of the amount of methods that have been developed that uses this assumption, I would argue that this is an example of an assumption that has become entrenched in the process. And there have been papers, there have been empirical studies that have been trying to show that in fact we can interpret activities of cortex, for example, visual cortex, as representing the statistical properties of visual input, so the probability distribution over visual input. And in this process of entrenchment of modeling choices, we run the risk of raifying them and treating them as something that exists in the world. So in this case, it's unlikely. well, maybe we have mathematical Platonists in the room, but for all the materialists here, I don't think anybody would say that there are probability distributions in the world. This is a tool that we use to describe the world, and
we don't talk to mathematical Platonists.
Yeah. So in this case, this kind of assumption that in the brain there are probability distributions is in fact a reification of this modeling choice that has been made to enable the use of particular methods for describing the operations of the brain and the cognitive nature of humans. So another example that comes from DFEM of a modeling choice that has become also entrenched. But this is mostly to just substantiate what I'm talking about, is the assumption made in active inference that we can talk about the minimization of free energy only on average and in the long run. And this has later, as I said, become entrenched in the form of the expected free energy term in the novel, more recent versions of the free energy principle. And in this case, we kind of the idealization that is made is about the proper time scale on which we should be discussing the operation of the brain. For rational constructivism plus, an example of idealization or modeling choice that is being made is that from Ullmann and et al. 2012 paper. Okay, that I will try to briefly get in a second. In that intuitive theories are generative models defined over hierarchies of structured representations. And we see here two pieces that are already our modeling choices. So intuitive theories in children are unlikely to actually be, but we choose to model them as generative models defined over hierarchies of structured representations. And maybe I'm not so, yeah, so the symbolic representation part, whether this is an idealization or not, I will not argue because I don't think we have room for that today, but it could be also treated as that. So important differences between FEP and RC, which also go back to the distinction that Mel has introduced between the Re and the Wiktor top-down, bottom-up axis, also cuts across the different types of idealizations that are being made. So just as a brief case study, I will probably just go through the first one. So I've chosen this paper from Fleming, Steve Fleming from 2020, Awareness as Inference, where Fleming provides a model of the phenomenon that can be described in a simple sentence as the difference between reporting I am aware of X and I am unaware of X. So in general, this is the model of access consciousness, if you will. And formally, he describes the process responsible for that on an algorithmic level, because this is an algorithmic level, as a probabilistic graphical model with nodes corresponding to perceptual states and contents of perception. And he tries to make a case for a comparison to empirical data in qualitative terms, and takes, there's a typo there, the algorithm is interpreted to produce global ignition patterns, and he runs simulations of his model, and he shows that when we quantify the amount of prediction error across two different cases where the model reports being unaware of a percept and when it reports being aware of the percept, because of the specific way that the perceptual state space is compartmentalized in the process, there is this large amount of difference in the prediction error. So the blue line indicates seen. It's on the screen. So and he takes this kind of difference in the amount of prediction error to correspond to global ignition patterns that are a major principle of global workspace theories of consciousness. And in this sense, we can see how this kind of like high-level free energy principle-based approach allows for devising an algorithmic model, which then is able to provide from top down an explanation of a bottom-up phenomenon in which the particular mechanisms in the brain give rise to awareness via global ignition. And I think I will stop here.
Okay, great.
Yeah.